In this unit, we're going to be talking about differentiation of logarithmic functions. That is, talking about how do we find the derivative of a logarithm. Now, before we even begin, you may want to recall that a logarithm is the kind of function that has a vertical asymptote, simply because it is the inverse of an exponential function, and the exponential functions had the horizontal asymptote, and our domain and range switch. So we have a vertical asymptote. Here's a graph of y equals natural log of x to illustrate that point. And as x approaches the value that defines that asymptote, the value of the logarithm itself will tend towards positive or negative infinity and grow without bound. Here's a good example of that. Let's consider the graph of y equals the natural log of x, which I've shown below right here. As x approaches 0, what's going to happen? So let's consider a limit, at least in this case, based on our definition off to the top over here, that as x approaches 0 from the right of the natural log of x, and you can get out a calculator and verify this for yourself, but as we choose values of x that get closer and closer to 0 without actually being at 0, right, because our domain right here is the set of all values of x that are greater than but not equal to 0. So I'll write this in the set builder notation over here. The set of all x such that x is greater than but not equal to 0. We ask, what will this limit do? Well, as x gets closer to 0, if we start at 1, y is equal to 0. Now, because it's the natural log of x, we could put in 1 over e, which is a fraction that's close to 1/3, and we get negative 1. We could take 1 over the square of e, which is a number that's about, pretty close to, let's see, 1 over e squared. E squared is 2.7. It's going to be close to 1/9. Negative 2. And as we choose values of x that get successively closer and closer to 0, we can see from the graph, right, as we get close to e cubed right here, we get to negative 3, that the y values start increasing in the negative direction without bound towards negative infinity, even though the x values themselves get closer and closer to 0. So this illustrates that our limit here must be negative infinity. In other words, it's going to grow without bound in the negative direction. So what implications does this have for us? Well, we will be asked to evaluate limits like this one. Evaluate the limit as x approaches 2 from the right of the logarithm. This will be the common logarithm of the quantity x minus 2. What happens, Mr. Peoples? Well, in this case, I'll tell you that the way we're going to evaluate this is first to recognize that the domain of this function is found by setting the argument x minus 2 greater than 0 and solving for x. And of course, that is all x greater than 2. Not only that, the domain corresponds to the location of our vertical asymptote, which is found by setting our argument equal to 0. Right? And x minus 2 is equal to 0 at the point x equals 2. So x equals 2 is a vertical asymptote, and we approach it from the right. And so we can see what's going to happen right here is basically the same thing that happened in our other limit. As we let x approach 2 from a value slightly greater than 2, what's happening is that the y value, or the logarithm value, is approaching 0. That is, the argument, and I'll indicate it this way, the argument is one in which we're taking something slightly greater than 2 and subtracting 2 from it. So we're going to consider this to be some very, very small positive number. And whenever we take a logarithm of a very small positive number, we come up with a very large negative number. That is, this tends towards negative infinity. And so this is our limiting value right here for a logarithm. Something to keep in mind as we move ahead into the section.